Hello, ladies and gentlemen, boys and girls. Welcome to our little math theater. Today we want to look at lesson 1.5, limits. And we want to go over some of the examples we have in our lesson plan. And so you'll be able to follow along with me. And if you have to rewind the tape, pause it, to go over it again, I encourage you to do so. And so in this lesson, we want to highlight some of the major points. And so we want to look at finding limits of functions graphically and numerically, using different analytical techniques to evaluate limits, use property of limits to evaluate limits, and we want to also evaluate limits involving trigonometry. So we're going to take a look at all of these various techniques. So I'm going to go over some of the example problems, and I want you to follow along and work them out with me. Okay? Let's go. Disregard the due dates and all this information right here. We'll get to this in class. This is support I'm giving you now is for outside of class. We'll get to this in class. Okay? Alright, let's go. Okay. So first, we have the limit of a function, two graphs here, that explains exactly what's going on in terms of finding the limit of a function. And then we have example 1. Let's do example 1. Let's look at our examples. Find the limit. The limit as x approaches 1 of x squared plus 1, that quantity. What's the limit? Well, in this case, we want to use what we call direct substitution. Use direct substitution. So go ahead and take 1 and substitute 1 into x. And let's see what our output is going to be. If we do that, this is going to equal 1 squared plus 1, which equals 1 plus 1, which is 2. And that's it. That's the answer. So the limit as x approaches 1 of x squared plus 1 is 2, by way of direct substitution. Okay, let's go further. Find the limit as x approaches 5 of 2x minus 7. Okay. Again, direct substitution. Always try that first. Let's see. So we're going to have, this is going to equal 2 times 5 minus 7, which is 10 minus 7, which equals 3. So the limit as x approaches 5 of 2x minus 7 equals 3. Ta-da! That's it. 3. By way of direct substitution. Okay? So that takes care of the first two examples. How to find the limit. Alright. Let's move on to our next example. Let's go forward. Example 3. Alright, in this case, find the limit. Limits may also exist at a point on a graph where the output f of x is a different value. That makes sense. Watch this. Come on. Come and go with me. Watch this. First, I'm going to extend my y values. We have 1, we have 2. I'm going to make this right here. I'm going to make this 3. I'm going to make this 4. I'm going to make this 5. Okay, so 1, 2, 3, 4, 5. Okay. And 1, 2, 3. All right. Good. Good. And so here's what we're saying. Watch this. Look at this. When x equals 2, if x is 2, the x value here is 2. When x is 2, then what's y? What do you think? When x is 2, y is 5. So we have the coordinate point 2, 5. When x is 2, y is 5. That's our coordinate point, 2, 5. However, that is not the limit. That's not the limit. Okay? So in this case, what is our limit? Well, let's see. So for this graph, the limit as x approach 2 of this function here, I don't know what the function is, let's call it f of x. As x approaches 2 of the function f of x here in blue, then what is the limit? What's the value of the limit? Okay, it's not 5. The graph f of x here, coming from the left and coming from the right, approaches this number right here, or this value here. The value it approaches is 3. That's the y value that's being approached. The y value that's being approached is 3. So there you go. The limit is 3. Because that's the value that we are approaching from the left and from the right. The value, the y value is 3. So as x gets close to 2, as we get close to 2, we're approaching 2 on the x-axis, the function f of x approaches 3. It makes sense. This graph here does not approach 5. The graph as x approaches 2 approaches 3. So the answer is 3. Same thing in this case. Watch this. Same concept. Watch this. Okay? Now we know this dotted point right here. This point here, that is the point 1, go over 1 and then don't move. 1, 0. That's this point. But the limit is not 0. It's not 0. Let's see what the limit is. Here we go. The limit as x approaches, well, what is x approaching? X is approaching 1 along the x-axis. That's 1. Of f of x. Well, as x gets close to 1, what does my graph, what does f of x approach? As this happens, what happens to the function f of x? Well, as x gets close to 1, the graph itself, the graph is approaching what y value? What y value am I approaching? Oh, the y value is 1. So there's your limit. There you go. So as x approaches 1, f of x also approaches 1. And not 0, but 1. It's all about that y value. what y value is the graph approaching as x approaches a value. Okay? Yeah. Okay. Let's keep it going. Let's go. All right. Example 4. All right, now example 4, these type of functions are called hiccup functions. You ever have the hiccups? You know, hiccup functions. Okay? Let's take a look at the hiccup. All right? And so the limit as x approaches 0 of f of x, here's what it equals right here. All right? Check it out. First, let's consider a graph. A coordinate plane. I'm sorry, not a graph, a coordinate plane. A coordinate plane with an x-axis, of course, and a y-axis. There we go. Now let's look at two separate functions. Let's look at f of x equaling 1. Okay? So first let's consider f of x equals 1. See? F of x equals 1. Okay? Where x does not equal 0. Okay? F of x equals 1 for x not equal to 0. There you go. Let's graph this. Graph that. Let's graph that. Now, f of x equals 1, that's the same thing as y equals 1. So this also can be considered simply as y equals 1. Let's graph the function y equals 1 with no x value at 0. All right, here we go. Let's graph that. So here's 1 along the y-axis. This is the number 1. So y equals 1 is going to look like this. This right here is the graph y equals 1. Yay! Now, for this graph y equals 1, x cannot be 0. So go to the x value at 0, which is here, and there has to be a circle or a hole in the graph. So I'm going to put a hole right here, an open circle. Why? Because x cannot be 0. So at 0, I have an open circle like this. Open circle. This function is not defined where x is equal to 0. There's nothing there. It's an open circle. It's a hole. It's a gap. It's discontinuous right there. So that takes care of my first graph. Now let's consider the second one, which says f of x equals 2. All right? F of x equals 2. For x equals 0. Okay. So this means f of x is the same as writing what variable? Y. So y equals 2. And what does x equal? 0. Oh, wait a minute. I recognize something. That's a coordinate point. That's just the point 0, 2. Because x is 0 and y is what? 2. Look. 0, 2. And that's it. Plot that. That's pretty easy. Let me see. 0 and go up 2. 1, 2. Here's 2. So this point right here is the point 0, 2. All right, that's done. So now we're ready to find the limit. We can find the limit now. All right, so the limit, let's do that. Let's find the limit. Let's go get it now. So the limit as x approaches 0 of f of x, which is 1 for x not equal to 0, and 2 for x equal to 0. This limit has to equal, well, let's see. As I come from the left, I'm approaching 1. As I come from the right side, I'm approaching 1. So the limit is 1, not 2. It's not 2. It's 1. Because the graph coming from both directions is going toward the y value of 1. That's the metro station. All the buses coming from both sides. You have a bus coming in from the west and a bus coming in from the east. They're coming to that one metro station right there. And the station has a y value of 1. The bus is coming on the path. Okay. So the limit here is equal to 1. Okay? Alright, let's move. We have to keep it moving. Now, if at any time you need to, pause the tape, stop the tape, rewind, hear it again, please do so. Okay? Or just ask me in class the next day. Alright? Okay. Let's go. Let's see here. Alright. And now we have limits that do not exist. Okay? Take a look at this limit. Non-removable discontinuities and will result in limits that do not exist, vertical asymptote and diving boards. A lot of these phrases, again, I will explain in class. The purposes of these series, the tapes, is just to go over with you the actual examples. I'm just going over the examples right now, so you have a better understanding of how to do the examples. Alright? The diving board problem. Piecewise function. Oh no, I'm sorry. We're doing this one. The vertical asymptote function. The limit as x approaches 0 of 1 divided by x squared. Well, what does that equal? Well, notice this. As I come in from the left side, I go to positive infinity. This is going to positive infinity. As I come in from the right side, this is also going to what? Positive infinity. Infinity is not a value. Okay? It's not a value. It's not bounded. It's nothing really tangible. You can't put your hands around it. You can't feel infinity. It just keeps going and going and going like the Energizer Bunny. And so the limit as x approaches 0 of 1 over x squared, the answer is positive infinity, which in fact, what? Does not exist. Simply put, D N E. Does not exist. And it doesn't exist because you can't put a value to infinity. Okay? There's so many values in infinity, going out toward infinity, wherever that may be. You just can't bound it. So that doesn't exist. It goes toward positive infinity from the left side and from the right side. Okay? So that's our vertical asymptote problem there. So that's what we have right here. We have a vertical asymptote at x equals 0. All right. Let's move on. Determine the limit for f of x equal, 0 if x is less than 0, and f of x equals 1 for x greater than or equal to 0. Piecewise function here. No problem. Split it up. Take a look at each function separately. Alright, so first let's consider f of x equals 0. F of x is 0 when x is less than 0. Let's graph that. Well, if I graph f of x equals 0, remember, f of x is like saying y equals 0. Let's graph y equals 0. Okay? Y equals 0 is the x-axis. Here you go. There it is. This is the graph y equals 0. Okay? So this part is done. There it is. Now, I do not want the entire line f of x equals 0. I have a restriction or conditions here. The condition is I only want x less than 0. And so the x value I'm concerned with is 0, which happens to be right here. And I want the values that are less than 0. Less means left, right? So I want the values that go to the, make an arrow here, left of 0. Left. Not including 0. So at 0, I cannot include 0. I will have an open circle at 0. And everything to the right of it, I must get rid of. All right. That takes care of f of x equals 0 when x is less than 0. There it is. So this part, or this piece of the piecewise function is graphed. Now I have to look at f of x equals what? 1. When x is greater than or equal to 0. Let's do that piece. All right, here we go. F of x equal 1. All right, when x is less than or equal to 0. So first let's graph f of x equal 1. No problem. All right, we're going to do that in our color here. Let me see. Here's 1. Let's graph the whole thing. All right, there you go. This is f of x equals 1. All right, that's f of x equal 1. The whole entire line. Do we want the whole entire line? That's right. No, we don't. We only want the portion of it where x is greater than or equal to 0. So that means you want to include 0 because it's greater than or equal to, and make an arrow here, which means you want the piece going to the right. So I want to include 0, and then only the piece of it going to the right. So everything to the left, I don't need. So erase what's going to the left. Or you can look at it like this. There cannot be any overlap, okay, between the gold and the red. No overlap. And so this is overlapping. No overlap. So erase that piece. Cannot overlap. And so now we're ready to determine the limit here, even if we have an existence of a limit. It doesn't exist. Here we go. So the limit as x approach 0 of 0 if x is less than 0 and 1 if x is greater than or equal to 0. This limit equals, well, let's see. Let's see what it equals. as I go to 0 this way, what is my value? What's the y value? As I go to 0 from this direction, what's the y value? The y value is 0. So on this side, I'm going to have 0 as my y value. Okay? So on this side, I get y equal 0. If I come in from this side, as I get close to 0, what's my y value here? The y value is 1. We have a problem. 0 does not equal 1. So this limit does not exist. Does not exist. Doesn't exist. Now, if you're still saying, wait, Mr. Wright, I still don't get it. Okay, look at it like this. In order for a limit to exist, I'll go back to the example I used last time. Let's look at it in terms of the bus station or metro station, okay, or the ride-on station, I guess. If you are familiar with metro, you catch the bus, okay? Notice this. As this bus here comes in to the station, right? The station is right here. As this bus comes into the station, the station is up here at 1. The buses can't go to 2 different stations. If the limit is going to exist, the buses must go to the exact same station. And if they go on to 2 separate stations, then the limit does not exist. That's what's happening here. Bus A is going to this station, bus B is going to the other station, therefore no limit. They must go to the same station. All right. Does not exist. Let's move on. Does not exist. The limit of a polynomial function. Pretty simple, not too bad. Go right back to what? Direct substitution. You got this one. Directly substitute. So, when we put -5 in for x, we're going to have get -5 quantity squared. Let's do a bracket here. -5 quantity squared minus 3 times -5 minus 35. And then just do the arithmetic here, and you'll be all right. All right, so we're going to get 25 plus 15 minus 35. And this is going to give us, well, 25 plus 15, that happens to be 40, minus 35. And 40 minus 35 happens to be 5. Piece of cake. All right. Remember, we use what? Direct substitution. Okay. All right. The limit of a rational function. Rational meaning that we have a polynomial numerator, polynomial denominator. That's what makes it rational. Polynomials are both numerator and denominator. Okay, again, direct substitution. As a approaches 1, take 1 in for a, substitute it in. 1 squared plus 1 plus 2 divided by 1 plus 2. And that's going to give us 1 plus 1 is 2, plus 2 is 4. 4 over 3. And here's our answer, 4/3. Okay? the limit of a radical function. There's the radical. Take 3, directly substitute 3 into the function. Square root of 2 times 3 squared minus 2 gives us the square root of 2 times, well, 3 squared is 9, minus 2, which gives me the square root of 18 minus 2, which gives me the square root of 16, which happens to be 4. All right. Good. 4. Good. 4. Oh my. Someone looking at this just became very, very sick. I know. You thought you were getting away from the unit circle, didn't you? Oh no. It's back. The unit circle. Oh. Knowledge of the unit circle is very important. Okay? And so we have our various angles here, 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 120, 135, 150, etc., etc., etc. You have all your angles going around the circle, and you have the cosine and the sine of each of the angles, and radian measure and degree measure. Radian being here, and degree being here, and the values of them being here in parentheses, the values. Okay? So you have to go back and familiarize yourself with the unit circle, because it's not going anywhere. It's here to stay. All right? Let's go to work. Let's see. All right, so first, let's evaluate the sine, the limit as x approaches 0 of sine x. Direct substitution. So it's going to equal the sine of 0. Put in 0 for x. And what is the sine of 0? Well, let me see. When my degree measure is 0, when my radian is 0, what is the sine value? Well, this value right here is cosine, let's say theta, well no, 0. And this value right here is the sine of 0. So it's obvious to me, and to you also now, that the sine of 0, this 0 is here. Say radian measure. That's this 0 right there. The sine of this 0 equals this 0. Example 6. The limit as theta approaches pi of theta cosine theta. So now we're putting in pi for theta. Put pi in for theta. What do we get? We get pi, the cosine of pi. So put in pi for theta. This is going to equal what? Pi times the cosine of pi. What is the cosine of pi? Well, first, let's find pi on the unit circle. Oh, here it is. There's pi right there. So here's pi on the unit circle. And so this value right here, this is the cosine of pi. And this value right here, 0, is the sine of pi. And so the cosine of pi, see look, cosine pi happens to be -1. So now it's going to be pi times -1, which equals negative pi. As long as you understand the concept of what's happening here, the big picture, you need the big picture of what's going on. All right, let's keep moving. All right, you can try this one on your own, or we'll come and do it in class. We'll cover that later. All right, now we want to evaluate or look at techniques for evaluating limits when what? Direct substitution doesn't work, producing the indeterminate form 0 over 0. Everything we've done so far, other than the piecewise functions and diving boards, all the other limits, we just plug the number in, we directly substitute. See? Direct substitution, that's what we've done so far. Now we're going to look at functions in which we cannot do what? Direct substitute without getting an indeterminate form. So there's other techniques that we're going to have to use in order to evaluate. Okay? So, let's get started with the first one. The cancellation or the factoring technique. Let's do that. First of all, if I put -3 in for t, the limit as t approach -3, let's try direct substitution. Let's see what happens. Let's just put it in. Let's see what we get. Let's just try it. This is going to give me -3 squared plus -3 minus 6 over -3 plus 3, which equals, up here I want to get 9 minus 3 minus 6 over -3 plus 3, which equals, well, 9 minus 3 is 6 minus 6 over -3 plus 3, which equals 6 minus 6 is 0, divided by -3 plus 3 is 0, which gives me 0 over 0. 0 divided by 0 is called the indeterminate form. We cannot determine, at least right now, what's going on. Okay? We cannot determine whether the limit exists or not. We cannot say here that 0 over 0 equals 0. Not true. 0 divided by 0 does not equal 0. 0 divided by 0 is what we call indeterminate. It's indeterminate. And so when we have the indeterminate case, we have to use other techniques to find the limit. And the first technique we're going to look at is called the cancellation or factoring technique. Let's go get it. The cancellation or factoring technique. So what we have to do in this case, we have to factor the numerator. So we're going to have the limit as t approaches -3 of factor the numerator. Okay. T plus 3 times t minus 2 all over t plus 3. So now our numerator is factored. You see that? Now it's factored. And then after we factor it, then we can do what? There's the word. Cancel. Cancel out. Let's cancel now. Oh, look. T plus 3, T plus 3, they both go to 1. So now I'm going to have the limit as t approach negative 3 of t minus 2. Now go back to direct substitution. Use the technique, factoring, cancel out. Now it's time to go to direct substitution. This is going to equal negative 3 minus 2, which is negative 5. And so that's our limit, negative 5 in this case. That is the cancellation factoring technique. Okay? All right, let's go forward. All right. All right. And then there's something called the rationalization technique. All right. Now, whenever you're going to rationalize the numerator or denominator, we must multiply by a convenient form of 1. A convenient form of 1. The convenient form of 1, for an example below, is 1 equals the square root of x plus 1 divided by the radical x plus 1 plus 1. You have to do what? Multiply by this. Let's multiply by this. Here we go. And so the first thing we want to do is take what we have here, our numerator here, and multiply it times 1, or the conjugate of this numerator, of the numerator. So it's going to be the square root of x plus 1. Notice I rewrite the same thing under the radical. The only change is, don't write minus 1. Write the opposite. Plus 1 divided by the square root of x plus 1 plus 1. Now it's time to multiply. Okay? Maybe I shouldn't have this 2 right here, because by default, if you don't see a number, we know it's a 2. Like we know there's a 2 here by default, it's square root. Okay? So now we have to multiply. You need to recall something. Recall from Algebra 1 that a minus b times a plus b equals a squared minus b squared. Okay? The difference between two squares are here. Here are the factors of the difference between these two squares. One factor is a minus b, the other factor is a plus b. So these two things here in my numerator are factors. So when I multiply them together, I get a squared minus b squared. I'm going to call this a, and 1 over here is b. So when I multiply my numerators, I'm going to get the square root of x plus 1 squared minus 1 squared. Because this numerator times this numerator follows a minus b times a plus b, which is a squared minus b squared. This is a squared minus b squared. All divided by x from right here times all of this times the square root of x plus 1 plus 1. We're on our way. You have to keep multiplying. We're on our way. Okay, let's go. And so now what happens? Well, what is x plus 1 quantity squared? Well, square root, radical x plus 1 quantity squared. Well, the radical symbol and the square cancels out. So you're just left with x plus 1. Minus, well, 1 squared is simply 1. Divided by, don't multiply this through, just rewrite it. X times the square root of x plus 1 plus 1. Keep simplifying. Well, look, in my numerator, I have a plus 1 and a minus 1. They do what? That's right, they cancel out. So I'm going to have x right here, all divided by x times the square root of x plus 1 plus 1. All that in bracket. Good. Equals. Can you cancel anything else out? What else cancels out? Oh, I have an x in my numerator and a lonely x out here in my what? Denominator. The x's cancel out. And so, this x here goes to 1, and this x here goes to 1. So I'm going to have now 1 over the square root of x plus 1 plus 1. Limit as x approaches 0. After all that rationalization is over, now it's time to go back to what? Direct substitution. So use the technique first, and then go back to direct substitution. The technique was rationalization, multiplying by 1, writing it in a what? Convenient form. We did that. We multiplied by 1. And at the end, after you rationalize, after you've gotten rid of, if you will, my radical and my numerator is gone, rationalization's over, now go back to direct substitution. So now plug in 0 for x. If we do that, we're going to get 1 over the square root of 0 plus 1 plus 1, which equals 1 over the square root of 1 plus 1, which equals 1 over 1 plus 1, which is 1 over 2, a half. There you go, there's your limit. So the limit of our problem equals a half. So, the limit as x approaches 0 of the square root of x plus 1 minus 1 over x equals 1 half. Rationalization technique. Sometimes direct substitution doesn't work and you have to do what? Rationalize. How you know when to do that? Look for the radical. Look for the radical symbol. And you say, oh, I've got to rationalize. Yay, such fun, right? Alright. Let's move on. Another technique. Trig re-expression technique. Okay? First, let's show and prove that direct substitution does not work. I'm sorry.